Problem solving. Stainless steel is an example of a substitutional interstitial alloy. It is an alloy of iron, chromium, nickel, and carbon. Which added elements are substitutional? Which are interstitial? Explain. Both chromium and nickel atoms are similar sizes to iron. These elements would act as substitutions for iron atoms in an iron crystal lattice. Since carbon is so much smaller than iron, it would act interstitially. Carbon will occupy the voids within the iron-metal arrangement. Explain the following trend in lattice energy. Magnesium fluoride has a greater lattice energy than magnesium chloride, which is greater than magnesium bromide, greater than magnesium iodide. Check out the periodic table and find out that from fluorine to chlorine to bromine to iodine, they're going down a period. That means their ionic radii are increasing. So as the radii increase, the Coulombic force between the anion and the cation decreases. Less attractive force, less lattice energy. Use lattice energies to explain why magnesium oxide is much less soluble in water than is calcium oxide. The magnesium ion has a smaller atomic radius than the calcium ion, and you find that by looking on the periodic table. So magnesium oxide has a higher lattice energy than calcium oxide. Since it has a higher lattice energy, it is more difficult to break apart the ions in magnesium oxide than it is to break apart the ions in calcium oxide. Therefore, magnesium oxide is less soluble in water than calcium oxide. Classify the following solids as molecular solid, ionic, metallic, or covalent network solid. Phosphorus pentoxide is a molecular solid. It has covalent bonds and is a nonmetal. Graphite, a covalent network solid, covalent bonds, and it's based on silicon, or in this case, carbon. Brass, metallic, it's an alloy, mixture of metals. Silicon carbide, a covalent network solid, covalent bonds, in this case, based on silicon. Rubidium, that's a metal, so it's metallic bonds. We have molecular iodine here, I2, that's a molecular solid, covalent bonds, and a nonmetal. Lithium bromide, ionic bonds. Molecular phosphorus, that's a molecular solid, has covalent bonds, and it's a nonmetal. Sodium sulfate, ionic bonds between sodium and the sulfate there. And copper is a metal, metallic. Put a check there. It's not letting me check. There we go. List 3 ways in which the properties of metallic solids and ionic solids are different. Appearance. Metallic solids are more highly reflective. Malleability. Metallic solids are malleable. Ionic solids are brittle. Conductivity. Metallic solids conduct electricity. Ionic solids are insulators. Use diagrams to help you explain why metallic solids are malleable, ionic solids are brittle, and covalent solids are soft. In each case, we're going to apply pressure to the metallic solid, to the ionic solid, and the covalent solid. When you apply pressure to a metal, it will shift the lattice, but not change any forces between metal atoms and their sea of electrons. So they will be very malleable. Pressure applied to an ionic solid causes a shift in the lattice, which aligns like charges. See, we've got 2 positives facing each other, 2 negatives facing each other. That will result in repulsion and breaking. And finally, for the molecular solid, it easily breaks, the pressure applied easily breaks the weak intermolecular forces holding the solids together, so they're very soft. Molecular solids and ionic solids are good insulators, while mechanic solids are poor insulators. Explain why their respective types of bonding give rise to this difference in properties. Metallic solids have a sea of electrons bonding structure. The metal atoms form a lattice based on Coulombic attractions for one another, while their valence electrons are free to roam about the positively charged ions. And then when you apply a voltage to that, the electrons move, which is a current. In contrast, molecular solids and ionic solids have no free electrons. Valence electrons are strongly attached to their nuclei, so the electrons won't flow in a current very easily, if at all. Graphite, graphene, and diamonds are all allotropes of carbon, yet graphite is soft, diamonds are hard, and graphene is strong. Graphene and graphite are semiconductors, while diamonds are insulators. Explain why these solids, all made of carbon, have such different properties. Graphite, graphene, and diamond are all covalent network solids. They have regular crystal structures that are all different from one another. They have different bonding patterns and arrangements for the carbon atoms in space. Diamond has carbon atoms bound together in a three-dimensional lattice. Graphite is layered graphene. A small amount of pressure separates the layers of graphite. Graphene is a two-dimensional lattice of carbon atoms. Graphite and graphene's carbon atoms participate in three covalent bonds, leaving the fourth valence electrons free to move about the lattice. And that will make them conductive. The bonding structure of a diamond has each carbon atom participating in four covalent bonds. There are no free electrons. Solids A and B are composed of silicon and oxygen in the same fixed ratio. Both solids were analyzed by X-ray diffraction. Solid A gave no particular diffraction pattern, while solid B gave a very consistent X-ray diffraction pattern shown here. See the bright spots there? Identify the types of solids and discuss the differences in structure between solid A and solid B. And here is the solid, that's the crystalline solid right there. And here you have the X-rays going through, and that will diffract them, giving a pattern or not giving a pattern. And that's covered in physics, this stuff here, X-ray tube source over here. Because solids A and B are both made of silicon and oxygen, they are both covalent solids. Because A gave no particular diffraction pattern, it has no regular lattice structure. That indicates it is an amorphous covalent solid, such as glass. Because B gave a regular pattern, it must have crystal lattice structure and is a covalent network solid, such as quartz. Use Coulomb's law to explain the melting point trend in the table below: sodium chloride, lithium fluoride, and beryllium oxide. Atomic radius determines the distance between the positive and negative charges in an ionic lattice. The smallest combined atomic radius is between beryllium and oxygen, followed by lithium and fluorine, followed by sodium and chlorine. According to Coulomb's law, the closer the opposite charges, the stronger the lattice energy. So as R, which is the distance between the ions, decreases, more energy is required for atoms to leave the solid lattice and go into the liquid phase. So we have the melting point increasing in this direction as the ions get closer together.